Welcome to the lecture on formal languages and grammar. The study of formal languages started in the late 50s as a way to understand the translation of human languages. It was necessary to define a structure that enables a language sentence to be parsed to see if it meets the proper grammar requirements of the language. Formal language, which unlike natural languages, is specified by a well-defined set of rules of syntax. Rules of syntax are important not only in linguistics, but in the study of natural languages. But also in the study of programming languages, these rules are really important. In this lecture, we will learn about formal languages and their properties. More specifically, we will show that a grammar of the language defines the language, and languages are nothing but really machines. So we'll get started. So the first question we ask is, what is a computer? We think of a computer as a digital device that is able to execute some general purpose program on it. We are generally concerned about how fast the program runs or how much memory the program uses. Although they are important questions, we have not asked the most important question yet. That is, given a problem, can I write a program to solve that problem? If so, how fast, or how do we compute it? How do we do that? Or how much time or memory it takes? Then the next question to ask is, are there programs or problems that cannot be solved by a computer? So in order to answer these questions, independent of any machine, specific hardware, software, we need to define an abstract notion of a computer. The idea of defining the notion of an abstract machine was first developed by Alan Turing in the 1940s. The Turing's idea of a computer was called a Turing machine. A Turing machine is a mathematical model of the modern machine that contains two things. It is a machine based on a state transition diagram and a tape. We'll say more about this as we progress. So what you're learning in this course is the first exposure to the science of computer science. If you're a computer scientist, then you must know this. The benefit is the ability to abstract away details to solve difficult problems. In the next slide, you will learn, or next lecture, you will learn the notion of a finite state machine that explains a much harder and simpler way to build a machine to solve specific problems. So questions. Can we write a program to recognize all binary strings that ends in 0? So this is probably not hard to do. You can think of lots of different ways to do it. So we say, okay, yes, it is easy to do. Then we ask a harder question. We say, can we write a program to see if a given binary file, which is in zeros and ones, is indeed a Java program? How do you know it's a Java program? If you pass that binary file, can you generate the Java program that generated the file? The answer to that question is yes, but it's harder to do. And then we ask the question, can we write a program that checks if another program never gets into an infinite loop? In other words, we're asking the question, can we have a program that checks whether some other program doesn't get into an infinite loop? The answer to that question is no. So those are some of the questions you want to ask. The last question is particularly interesting. Are there problems that are undecidable? That's what we're asking. So we know that just thinking about these decision problems is a fine way to understand the theory of computing. So a Turing machine is a simple mathematical model that can be used to determine the computability of a function. So in other words, it's a mathematical abstraction of how we compute, and it is simple so we can prove things about what is computable. So next, we'll take a look at the notion of a language. So all languages have syntax, which is the form of the language constructs, semantics, that is the meaning of the language constructs, and natural languages contain these properties as well as artificial languages. However, natural languages can be ambiguous, and they're also context sensitive. So any type of a grammar that defines a language must be able to define or describe context-free and context-sensitive grammar. So formal languages, on the other hand, are defined by a set of rules, which we call syntax rules. These rules are well defined in order for that languages to be implemented on a deterministic machine. So we will study the properties of programming languages because they help us understand how compilers work and how a compiler might parse a programming sentence and understand its lexical validity. So once again, as we move on, we say formal language is a language that is a set of things that is specified by a well-defined set of rules of syntax. So we will ask two questions. How can we determine that a combination of words is a valid sentence in a formal language? This requires the sentence to be parsed and compared against the rules of the language. Then we can ask the question, how can we generate the valid sentence of a language given the rules of this language? So in the next few slides, we will study these ideas, not to a level covered by a course on the theory of computation, but just to get an understanding that languages are indeed machines. In other words, we can build a machine that can generate all sentences of a language and vice versa. So let's now define the notation of a vocabulary. In simple terms, vocabulary is a non-empty finite set of elements called symbols. The origin of these symbols is an alphabet. You can, for example, think of the alphabet of the English language, or for simplicity, you can think of the alphabet of binary alphabet, which contains 0 and 1, or the alphabet that contains ABC. If you study the alphabets with more than 2 or more symbols, the study would be very similar to studying alphabets with any number of things. Of course, the rules of the language defines what words can be constructed using this alphabet. For example, the set of words, all words that start with A and have exactly one A can be defined as AB star, for example. So we can say something like that. So in this context, the V star is essentially is the sequence of 0 or more characters from the alphabet. So it forms the symbols of this language or vocabulary. Now, the definition of a phrase structure grammar is a four-tuple, which is G equals VT SP, consists of a vocabulary V, and here the T is a set of terminal symbols. That means symbols that cannot be expanded further. And S is the starting symbol, and P is a finite set of production rules. So we have the vocabulary, and the T is the set of terminal things. The V minus T is really the set of non-terminals. In fact, V is the union of non-terminals and terminals, that is N union T. So elements of this set N are called non-terminal symbols. So you can have simple production rules, for example, that simply says that A can be replaced by B, where A and B are symbols from the language. Or can have a bit more of a good rule here. So if you have at least one non-terminal appears on the left of the rule, you can say a non-terminal can be expressed as either A, B, or C, or it can be N times N and A, which is another non-terminal. So it's sort of a recursive definition of a non-terminal. So you could have non-terminal ending with A or B or C and A. So let G be a phrase structure grammar. The language generated by G, or the language of these, is the LG, which is the set of all strings of the terminals that are derivable from the starting state S. So in other words, we can say that LG, or the language G, is the set of all strings from these terminals, such that those strings W's can be generated from the, starting with the S, the start symbol, and then applying it recursively to generate that. So this implies that you would apply 0 or more production rules to generate the W's that are in T star as a part of the language. So if you take the GB, the grammar, with a vocabulary of a starting symbol and 0, 1, instead of terminals 0 and 1, starting symbol S and the production rules, S goes to 1, 1S, or S can be replaced by 1, 1S, or S can be replaced by 0, we can ask the question, what is the language of this grammar? So you can clearly see that from the grammar, I can get 0 as a potential symbol of this grammar. And then if I use that S, 0 here, I could get 1, 1, 0 as a potential symbol of the grammar. If I apply that to, again, to the same rule, I can get 1, 1, 1, 1, 0 as a part of the symbol in this grammar. So soon you realize that this grammar is going to be either 0 or more 1, 1s followed by a 0. So this is something that we can explain using the rules of the language. So language is LG, which is a language derived by the grammar. And then once again, we showed that the language can be defined, generated from a set of rules that will create symbols in T star. So a sentence, if you look at the rules of English, a sentence is made up of noun phrase followed by verb phrase and so on. A noun phrase is an article followed by an adjective followed by a noun. So there are two definitions of noun phrases here. We could use either one to create a valid sentence of this grammar. So let's take a look at what sentences are possible by this grammar. For example, if you look at this problem here, say given a sentence, I can say a sentence is a noun phrase followed by a verb phrase. In this case, I use the noun phrase is made up of an article followed by the adjective followed by a noun. And a verb phrase is going to be a verb followed by, which is using this. Verb phrase is verb followed by an adverb. And now if I try to look for an article, article could be a or O, so I will use a. Adjective would be a large, so let's use large here. And a noun could be mathematician, that's a noun. And a verb could be eats. And then adverb could be quietly or quickly. So this should be quickly. So therefore we can pass the sentence, a large mathematician eats quickly, using these rules of this English. So here's a derivation tree based on the same grammar for the sentence, the hungry rabbit eats quickly. So we say this sentence is part of this grammar, generated by applying the rules repeatedly to get this sentence. So typically the sentences are derived from left to right. So basically you start with the non-terminals, sentence, noun phrase, verb phrase, and then you start to replace each of the non-terminals by a terminal, such as the. But you do it from left to right. So article is replaced, then the adjective is replaced, then the noun is replaced by rabbit, the verb is replaced by hops, and adverb is replaced by quickly. So essentially this shows you how the tree can be created by slowly replacing non-terminals by terminals. So general rules of derivation is that a simple rule of derivation is that A is replaced by B, indicating A is replaced by B. The more comprehensive rule of derivation is that A prime is replaced by B prime, where the arrow star indicates the reflexive transitive closure of this of the thing. So, for example, in mathematics, the reflective transitive closure of a binary relation on a set X is the smallest reflexive transitive relation on X that contains the relation. So in this case, we can derive from A, or we can we know that if we can derive B from A and then C from B, then we can derive C from A. So we call this the reflexive transitive closure. So there are 4 types of grammars. We're not going to study all of these things. We just need to understand that this was introduced by Chomsky in the late 1950s. So the 4 types of grammars are the type 0 grammar. It's the most unrestricted grammar, which has some simple rules of the grammar. In fact, this grammar is equivalent to what we call a Turing machine, which we will learn later. So in this grammar, the V can be replaced by, U can be replaced by V, where U is a string in V star. V star is a sequence of all the strings from the vocabulary. And N is a non-terminal, and again, V star is something like this. So in a type 1 grammar is what we call context-sensitive grammar, where the context alpha and beta is taken into consideration. For example, when we say put the chicken on the table and cut the legs, we could describe the sentence using some context, where the alpha beta plays a role in describing that will allow some languages to have a context-sensitive structure. So again, rules of the language are, we also call this length increasing. You go from U to a V, where the length of V is bigger than the length of U. So in other words, in a context-sensitive grammar, the empty string probably cannot be there because we couldn't find anything on the right-hand side. We couldn't get that. So type 2 grammar is, we can use type 2 grammar to describe what can be computed by a machine. They're more capable than a finite state machine, which we'll learn later, but less capable than a Turing machine. So a push-down automata is a finite state machine. So the rules of this are the important things for us, which says that if A is a terminal symbol, A can be replaced by some alpha, where alpha is a symbol from V star. It's a sequence of characters from V star. So that's a very simple push-down automata that can be used as a parser for language compilers. So type 3 grammar is a finite state automata, a finite state machine, that computes by transitioning from one state to another. For example, it can be in state A, in a state where it has seen a B, and now after seeing A, transition A from AB. So this means that probably perhaps it was in a state that you have seen something. Now you're transitioning into a state where you have seen A followed by what you saw before. So these rules are, finite state machines are the ones that we're going to be studying next. So again, there's no real detail that we were going to remove all the details about this, which you can read from the book to understand that. But essentially, understanding that the grammar are rules, there are rules that generate the grammar, and there are real things or machines or conceptual machines that can be equivalent to these grammars. In other words, you can say a grammar is a language, a grammar is a language, and a language is a machine. A machine is a language, and a machine is a grammar. We can make that equivalence, sort of equivalency between those two things. So each programming language is supported by a compiler that translates and executes language constructions in a form understood by a digital machine. There are 2 major components to a programming language. Compilers do analysis. One of the important things compilers do is what we call the lexical analyzer. So lexical analysis or tokenization is the process of converting a sequence of characters, such as in a computer program or web page, into a sequence of tokens, and then to check whether each token is a valid token in the language itself. So the parser essentially it's a syntactic analyzer. It's the process of analyzing a string of symbols, either in a natural language or in a computer language, and conforming to the rules of the formal grammar. Synthesis is the form of running the translated symbols through the machine, We're not going to focus much on that. So theory of computation is a huge area, which is one of the, perhaps the most theoretical area of computer science. So this theory of computation studies different types of grammars. They abstract models of various levels of computing devices. So some of the ideas you learn here about, for example, finite state machines are quite useful in developing simple algorithms for complex problems, such as string search. So a finite state machine is the most restricted machine that we can build. It can solve some problems, but not all problems. So for example, we may not be able to build a finite state machine that can count. So it doesn't have a lot of power, but in some ways, it's a very powerful machine. But you can add a little bit of power to create the outer circle, which is called the context-free languages. So it includes finite state machine plus a few more rules to make the machine more powerful. So essentially you add a little bit more capability using the rules to make the machine do more things. In other words, we can solve more problems once you have that. Then the outer circle is what we call the Turing machine, which is the full level of computing. Anything that can be computed can be done using a Turing machine. Turing machine is a simple mathematical model that describes the modern computer. Then finally, the outside circle is what we call the undecidable things. In other words, no algorithm can compute whether another program will not get into an infinite loop. So therefore, there's a whole class of things. If you take the theory of computing, you will see a lot of subdivisions across these things, and you might study a lot more things about the theory of computation. But our goal is to really give you like a basic background on these ideas. So next we will learn a particular grammar for describing syntax rules of a programming language called a BNF grammar. So what is BNF grammar? BNF, or Backus-Naur form, is a form of type 2 grammar, which is used to specify the syntactic rules of many computer languages, including Java. So let's take an example that for definition of an identifier. The set of rules that says the following. The left-hand side actually defines a terminal, and the right-hand side defines many options for each terminal allow us to build a lexical analyzer, a program that checks if a sequence of alphabet characters is in fact satisfy the rules of the language. So based on this, you can just say an identifier is either a letter, this is O, or an identifier followed by a letter, because so it's giving you a recursive definition with some level of a base case where you can get things started. Or it can be an identifier followed by a digit. So you will notice that if you follow these rules, all identifiers must start with the letter, because the letter must come first. Then you can have any number of letters and digits that follow this identifier. So workshop, what is the Backus-Naur or BNF form of the grammar for the subset of English described in the introduction to this section? So here's how we can answer that question. We said that sentence is a noun phrase, verb phrase. Noun phrase is article, adjective, noun, or article and noun. Verb phrase is verb, adverb, or verb. An article is either a or the. Adjective is large or hungry. Noun is rabbit or mathematician. Verb is eats or hops. Adverb is quickly and wildly. So BNF grammar can be used to describe the English sentences or past the English sentence that we saw before. So what is the BNF of a signed real number? So here's the answer. Signed real number is a sign followed by an integer, followed by a dot, followed by an integer. And a sign is either plus or minus. An integer is a digit or a digit followed by another integer. So you can see that using this definition, we could form an integer as a sequence of digits. This doesn't exclude the digit being at the beginning of the construction. But that's something you can worry about. You can think about that. So a digit is one of these guys here, and so on. So essentially we can strengthen this definition using an integer is something that doesn't start with a 0. So this is the end of it, and we will talk about final state machines.